iOS, JB, Present and Future. Jonathan Levin pondrá las cartas sobre la mesa sobre los sistemas de seguridad en el sistema operativo iOS de Apple, sobre cómo fueron evolucionando las vulnerabilidades para lograr el ansiado jailbreaking y sobre qué perspectivas hay sobre el jailbreaking más allá del iOS 12.
Okay, so what he said. Okay, people, thank you for coming. I know it's early on Thursday morning. Just before we start, I'm wondering how many people here have jailbroken their device at any given point? Oh, that's not bad. So for those people, I have some good news and some bad news, as we're going to be discussing effectively what jailbreaking is, and more importantly, what Apple is doing and trying really hard to prevent this. The topic of this talk is basically a review of jailbreaking up to the present point, which is going to be very quick, and then primarily focusing on the many defenses and the many changes that are coming, not just with iOS 12, but also the actual hardware changes that Apple really don't bother documenting or telling you about. Now, as you all know, jailbreaks have been pretty much since iOS 1.0. People, as soon as they realized what an amazing device an iPhone is, they realized effectively that people like to think of it as a mobile phone, but it's not really a mobile phone, it's a mobile computer. Generally speaking, iOS, or what they called it back then, iPhone OS, and Mac OS are effectively the same system. We're looking at a full operating system that can do multitasking, that can run applications, that can, of course, run SSH, and people want to liberate the iDevices to get all that functionality. Now, of course, over time, it's not just been iOS. There's now various flavors of iOS. There's iOS on the iPhone and the iPad, but we also have the TV OS, we also have the Watch OS, we also have the HomePod OS, which actually runs on the little speaker that nobody buys. They have the actual iOS running. And there's also, surprisingly, in the macOS Touch Bar, and even in some embedded devices that Apple uses, like, for example, the HDMI adapter that they do if you have a Mac or an iPhone Lightning to HDMI, that actually runs a small GNU kernel inside. Now, originally, jailbreaks were very simple. Back in the day when iPhone was first developed, nobody actually believed in Apple that it would be jailbroken. And then the first jailbreak happened. Apple learned from it, literally learned from it, as that probably helped them with the idea of the App Store, the idea of running third-party apps. And then following that, tried to harden as much as they could the jailbreaking process. And since then, it's been pretty much a cat and mouse game. Now, if you look at the timeline over here, you'll see that really it goes back a long time ago to actually even before I start. But as far as I'm concerned, iOS starts being manageable and usable around iOS version 3. And so you have here since version 3.2. And if you remember, back in the days, it was as simple as jailbreak me, where Comex was the first one to do this. They had a little website. You'd click on the website on a little link and you're jailbroken. It was really that easy. And at that point, it was that easy because really there was no need to touch the kernel. There was no need to actually do anything besides get a little bit of root access. And the main defense that jailbreakers are trying to get by, which is code signing, which enables them to run applications outside what Apple allows, was easy because they could just figure out what they call a syscontrol, and just toggle a variable in kernel mode from user space without having to go into kernel. The first major change was in iOS 5, where in iOS 5, obviously, they started hardening this stuff. And that's when we saw jailbreaks going also into kernel mode. And then, of course, Apple steps up the defenses. And the first defense was in iOS 6, which is called KSLR. Now, ASLR in general is a concept that now everybody uses in all operating systems. Apple was actually one of the first to use it in kernel mode, and that was the so-called KSLR, kernel address space layout randomization. The basic idea, you take the kernel, you just slide it by some type of value, which is usually around like 20 to 24 bits. So if you have any type of exploitable situation, at least in theory, the attacker doesn't know where they're going to get their ROP or their code execution, in which case, of course, you basically substitute panic for code execution. Now, of course, this was a welcome change, and also what they tried to do in 32-bit is use an ARM feature of SMAP, which is secure mode access prevention, which surprisingly didn't get into 64-bit until way later. But then that, of course, still was not enough, because we could find information leaks. Information leaks are cases where a system call or some type of driver call basically leaks information because it provides for you some type of data from the kernel, which is supposed to be proper data of, you know, some type of system call return value or system call buffer, but it copies too much or it uses uninitialized memory. And so that was used and is still used today to defeat KSLR in many, many ways. Then Apple realized that they have to change their entire model. And the very first, I guess, fundamental landscape shift that they had was when they introduced entitlements. And if you're familiar with iOS and macOS, entitlements are the basic like declarative security. If you're more of an Android person, think that every Android app has their own like manifest and permissions. Basically same idea, but instead of putting it in some type of manifest XML, we put it inside the code signature. And so they put in entitlements, and then following that came another landmark change which affects us to this day, which is KPP, which we will talk about. And this KPP is a so-called kernel patch protection. And if you have an iPhone device effectively from iOS 9 and later, then you know that this is one of the main hurdles to jailbreaking. However, it's only a hurdle, and hurdles can be bypassed, and this was repeatedly bypassed until around iOS 10, things started to really change as Apple shifted towards what we now see are hardware defenses. The first major hardware defenses that they put is something that they refer to internally as AMCC. It's also known as a code as KTRR, which is kernel text read-only regions, and now they refer to it formally as KIP, which is kernel integrity protection. And this is something that is from the iPhone 7 and later, which is what we call A10 devices. And as you'll see, we're basically fast forwarding to the present day, where in iOS 12 there's some changes, and in the A12, which is what's otherwise known as internally as the iPhone 11, or for us the iPhone 10s, 10R, 10s Max, whatever they call it, that's basically even more hardware protections, and we'll of course see all of that. Now just to get some basic ideas, because somebody at Apple obviously doesn't know to tell the difference between what a jailbreak is and what an APT is. So APT, that's Advanced Persistent Threat. You probably all know that. That's basically that targeted malware. And we've actually seen a case of that in iOS, if you recall or have heard about Pegasus, which I think is super popular here in like Central and South America. So basically, if you look at the actual distinction between an APT and a jailbreak, it's easy to confuse them because effectively they use pretty much the same techniques. In both cases, what we want is we want to get some type of effectively break of the security model. The only question is, do we actually use it for our own purposes, which is basically in order to infiltrate and then exfiltrate data and take out all the data of the device, compromise the device? Or if we want to do this in order to, say, be benevolent and beneficial and allow other people to use that as well. In other words, that's what we call jailbreaking. Now, the exploits required are basically the same. However, in practice for an APT, if I'm trying to get on your phone, I don't want to get root on your phone. I don't want to get kernel access on your phone. I'd rather get kernel access and root on some type of, backbone server or something in AWS. I don't need your stupid phone. Honestly, I can get one myself. And if it's really too bad, I can just always go to Android. So really, what people are interested when they're looking at APTs, they're only looking for one single thing, which is the very first step in jailbreaking, and that's a sandbox escape. Sandbox, because all your applications in iOS are third-party applications, are effectively quarantined and containerized, and therefore are very restricted in what they do. People want to unrestrict themselves. And the other thing in iOS, because everything runs as mobile or root, you only get two basic UIDs. So if you can break out of your sandbox and you're UID mobile, you can pretty much access any other app that you want. So all it takes is breaking that. And so if an APT desires to do its thing and get all of your contacts and get access to your camera and get access to your audio and so forth, that's pretty much it. However, for a jailbreak, at least a good jailbreak, the journey will just begin. And then there's additional steps that we need. The major step is a privilege escalation to get root access in user mode. Because as root access, you can do a lot more than just mobile. And you can basically access a lot of hardware devices, and you don't need any other specific workarounds that normally as mobile you would need. Then, most jailbreaks go that extra step. And that extra step is to go to kernel read-write. And once you have kernel read-write, you want to extend your benevolent powers to everybody and effectively patch the kernel or do some type of other type of kernel code execution in order to enable other applications to also benefit from various bypasses. Now, when it comes to persistence, unfortunately now what we have in the jailbreak world is something we call semi-tethered. We used to have untethered jailbreaks, which were that you could reboot your device into a non-jailbroken state. Then at some point we had also the tethered jailbreaks, which are those that rely on some iBoot vulnerability. If you remember back in the iPhone 4, we had that line rate and stuff. And unfortunately, we don't have those anymore. And so now we're stuck with something that as of 9.3.3 is basically the new normal, which would be the semi-tethered, when that means that your device reboots. It reboots into a non-jailbroken state. You have to click on some jailbreak app, and then you basically get your jailbreak back. It's a little bit annoying. It's further annoying because Apple has this thing that they only allow apps that are not App Store apps to run for 7 days before you have to re-sign them. But whatever, that's what we do. Now, the main thing that we want in a jailbreak, and I guess this is basically the difference between a jailbreak and APT, is the approach of unsigned code execution. In a jailbreak, you probably want your various apps, your tweaks like Cydia and all that jazz, and for that you have to bypass code signing. And bypassing code signing is really the most important step in some ways, because if you get that, and you'll see that in a bit, everything falls down. All of the Apple security model is effectively contingent on code signing. And then the other thing is those entitlements, declarative permissions, which in a jailbreak would be required, but again, if you're in an APT, you don't care about these things, so you just basically can bypass it altogether. So that gives us the view of what a jailbreak process is, and that's basically this very, very detailed flow chart, which I'm not going to go into the full steps, but basically the idea is that in order to get the initial execution on the device, we usually nowadays load the app, and that would mean side loading through like Cydia Impact or something like that. Then, that's one option. Another option is to exploit one of Apple's built-in applications. And for the built-in application, it doesn't necessarily have to be an application that you can see. There's a lot of other hidden applications, and even more than that, there are non-UI applications, which are generally daemons or processes. And if you can exploit one of those, that of course gets you the ability to effectively break out of the sandbox. And the other thing that might be an option is lockdown. And lockdown is a collective name that we use for when you connect your iDevice over USB, and then if you're familiar, you can run stuff through Xcode, or you can take screenshots, or you can see in iTunes your data and your applications. That's all done over lockdown services. Now, as you get into one of these vectors, your first step is to run your code. If you're loading an app, that's not an issue. If you're loading an app, you can basically sign with a developer certificate, and you got that. But at any point, you're going to have to go and reach that first step, which is the sandbox escape. And that sandbox escape is basically allowing your whatever app it was to get the full effect of unfettered file system access. At that point, you're going to have to do what we call a privesc, or elevation of privileges, and that's going to be to get normally the root permissions, but in Apple's case, there's also those bothersome entitlements that we need to get. At that point, you may or may not be reading the kernel memory, and you may or may not be patching the kernel. Again, we'll see in a second that patching the kernel is pretty much kind of like 2007. We don't do that anymore. But in some cases, what we do, and these are the little back arrows that you see here, there's a lot of shortcuts. And the shortcut is primarily that most exploits nowadays, and if you've been following, you see a lot of Ian Beer's exploits, the so-called TFP0, kernel task. That gets you automatic kernel read-write. And then from that automatic kernel read-write, you basically go directly, no need to escape the sandbox, because you can access the kernel through a system call or some IOKit method. And then, once you get the kernel read-write, you can just basically go back and then escape the sandbox and elevate your privileges and everything, because once you're in kernel mode, you're effectively done. You control the system, and all the checks and enforcements are done in kernel mode anyways. So, the modern day jailbreak that we have is primarily in iOS, not really 9, but 9.3 3 and later. First of all, they'd be deployed as a third-party app on the device with the developer certificate. You would find a vulnerable kernel attack surface, which is accessible from the sandbox, which means you do not need a sandbox escape. And then at that point, you're going to get kernel read-write, you're going to get the immediate profit, which of course, if you're an APT, you're pretty much done here. Otherwise, you're going back and you're doing all the other steps of entitling yourself, breaking the sandbox, blah, blah, blah. But this is just basically downhill from that point on, because there's really nothing more to consider at that point. The system has been fully compromised. Now, if we look at this from the Apple view, which is the defense mechanisms, and you'll notice here I say star OS. I use that a lot. That's for iOS, tvOS, watchOS. They're basically all the same. So we see that there is this first line of defense, which is, of course, Unix permissions. But unlike Android, for example, where every app gets its own UID, here, as I was saying before, there's either mobile, which is UID 501, or there's UID root. So that's your basic first line of defense. However, and this is unlike Android, that's when we get into a much deeper defense in depth. And so the main focus is, of course, going to be this sandbox that I keep referring to. And if I can refer to the sandbox something like, 10 times in the past 5 minutes, it's obviously something we have to deal with. The sandbox is going to be far more restrictive, and it's going to give us finer granularity on restricting operations, as you'll see in a second. Then below that, we've got entitlements, which are actually tying into the sandbox, because think of the sandbox as deny all, and then think of entitlements as yes, but allow this or that. And finally, underneath that, we've got code signing, which, as I was saying, is the main substrate. If you break code signing, you've effectively broken everything. From the kernel perspective, how is this all implemented? Well, with mandatory access control. Mandatory access control, what we like to call MAC, or MAC-F, for Mandatory Access Control Framework, is effectively the basic glue that holds everything together. Again, if you're coming from Android, my condolences, but if you are, you've got SE Linux or SE Android. It's basically the same idea. Unlike discretionary access control, which you can chown, chmod, chgrep, and change your permissions anytime you want if you root, mandatory access control is something that even root cannot change. So we have a user mode process trying to do some type of system call, trying to do some type of operation. This then goes into the system call table, or your mock-trap table for argument's sake. This then goes to the function. This then goes to actually invoke that function, but the function will not do anything until it calls out to this MAC framework. Now, what does this MAC framework do? In ZNU, absolutely nothing, because the framework is just a framework of callouts. In other words, the kernel proper does not care about whether you're allowing an operation or not allowing an operation. What does care is a list of kernel extensions which are called security modules. These security modules, we've got basically 2 of them in the main line, which are Apple Mobile File Integrity, which people like to not so affectionately call AMFI. And so this AMFI is going to do most of the basic but important checks on code signatures, and on process execution, and on certain types of entitlements, as well as debugging. Then, if AMFI says OK, then MAC-F says OK, then the system call says OK, then the user mode process gets a return and everything is fine. Otherwise, if AMFI tends to disagree with what you're trying to do, you're getting E-access denied and you can't do it. However, AMFI is not the only one. And there's actually a sequence of chaining where you can register MAC policy on any number of policies that you want. And in practice, the other policy that we have is the sandbox. And the sandbox has basically, if AMFI is only interested in about like 15 hooks, the sandbox is interested in about 150 or so. So 10 times the number of hooks. And virtually every little thing you try to do in your little app is something that the sandbox is going to inspect and decide whether or not to allow or to deny according to some type of profile. So overall, what we have here is like the, high-level view. Any questions, by the way? We all good? Okay. I mean, you're all like in the dark and there's so much smoke, I can't really see you, but, we'll try. So now we have the sandbox and we've ascertained that the sandboxes are basically number 1 enemy, so sandbox escape. How do we do that? We've got the sandbox and it's going to contain us. The way it works in iOS is a little bit different from the way it works in macOS. In macOS, it's actually pretty lax and allows you to do quite a few things because the idea is that in macOS you're like a power user. But in iOS, you're like a very restricted user, and you should be thankful every day for using iOS. So you should not try to hack it. So they basically define a built-in profile called container. And then when your app is deployed, it is deployed in /var/containers. Assuming iOS 10 and later. There's also var mobile containers, but let's agree that iOS 10 is our base. So in var containers, as soon as you try to exec a binary from var containers, it automatically, because of the path, starts with strcmp, it starts with that path, it automatically gets quarantined in Sandbox. Further, to make sure that you're not going to escape by like directory traversal, you cannot execute from anywhere in var besides var containers. On the root file system, yes, but in var, no. Var is like your data partition. So you have automatic confinement for all of your applications, whether or not you would like it. And then some Apple daemons may or may not decide to confine themselves as well. And that's done by actually a type of entitlement called seatbelt profiles. The name seatbelt is pretty much the original name of Sandbox. And the thing that makes this so hard is that Apple keeps on modifying and adding profile actions in every single version. And needless to say, they do not document any of this. So we've got basically the problem that these profiles are very hard to determine. Now in macOS, they're actually pretty easy. They're called SB profiles. And they're just basically in plain text. And let me just show you that there's two main locations for that. The first is System Library Sandbox, where if you look at System Library Sandbox, we've got /profiles here. That's one. The other is in User Share Sandbox. And in User Share Sandbox, there's even more of these little SBs. Now, taking any particular SB as, I don't know, like this KCM thing, so we can just go and see that there's a very well-defined profile language. That profile language is Scheme, which is a derivative of Lisp. Both languages are absolutely terrible. It's a course I had to take again when I did my comp sci, and I promised myself I'm never touching this again. And oh, the irony that now I have to touch it all the time. But anyways, you can see that this is effectively the language. If you see a lot of like parentheses, it's always Lisp. And just by looking at it, you can figure out just how very well detailed it is, which means it's got regular expressions, it's got very selective restrictions on which ports, which endpoints you can look at, and so forth. Again, if you're coming from Android, it's nice to compare this to the other operating system. Android doesn't have anything even remotely close to this. Yes, we have SC Linux, and yes, we have seccomp BPF, but we don't have the detailed argument inspection that you see over here. Now, the nice thing about in macOS is that these are, you know, Scheme, but you can at least read it. In iOS, that's not the case. In iOS, they're all compiled into the actual Sandbox text. And in that case, you have to decompile them. Now again, because profiles change in every single version, the decompilers break in every single version. There's one very good decompiler, which is called Sandblaster, and there's a bunch of tools that I wrote that enable you to compile, and when you compile, you can basically create your own profiles and see what they compile to. So it's kind of like a chosen plain text type of attack in order to figure out how to reverse this thing. So we have basically that Sandbox, we have a profile, but now we need to escape it. So how do we escape it? We've got two basic methods. I was saying already that the method that we normally use, that's the common method, is to find some type of service or some type of direct kernel IOKit or system call. Oop, that can, okay, that broke. That can basically be attacked through the Sandbox profile. So if you can get direct kernel attack surface, then that's fine. But that really is something that requires two things. It requires a kernel bug, which of course for which you're going to have an exploit, and it requires the visibility of that particular attack surface from your Sandbox, which may or may not be the case. There's a lot more kernel bugs than there are Sandbox accessible bugs. So method number two, which is actually number one in the slide, is to find some other type of service. We find a service that we can access over mock messages or XPC, which is basically some type of remote procedure call. And in doing so, we try to gain code execution there. And that's the general type of buffer overflow or integer overflow that you get in a message, which in turn turns into code execution through stuff like JOP and ROP and, you know, your favorite exploitation technique. So there's one other thing to consider, and that's a hardening measure they put in iOS around 10. Some of you in macOS may be familiar with SIP, System Integrity Protection, what they also call rootless. They have pretty much the same thing, only stronger in iOS, and they call it the platform profile. The platform profile is something that affects everything in the system, every single process, including launchd, including all the other processes, including Apple's own daemons. And that platform profile is basically fully restrictive, just like SIP. But unlike SIP, there's no CSR util that you can undo it. And so using this platform profile, you're basically doing the system policy, which says that you can only execute from various locations. I mentioned var containers as one, but also there's a whitelist for sbin, developer bin, user bin, and so forth. You can't do anything else. You can't execute third-party binaries now in iOS 11 unless launchd is the one executing them. That's a royal pain. And we've got system calls that you can't do unless you're somehow escaping this, for example, mount. And why would we need mount? Because one of the basic steps is to remount the file system, and you can't do that. So the only ways out of this would be the common way, which is getting kernel memory read-write and assigning yourself the kernel credentials. In other words, even though you're a user mode process, you're pretending to be the kernel. And the kernel is obviously exempt because the kernel cannot be checked because the kernel is the one doing the checking. So that's one. Number two is patching that platform profile if you can find it in memory and if you can figure out that Apple is not protecting it enough. And the last thing is to get entitlements. Because even though we've got this very restrictive profile, there's some utilities that still need to bypass that. For example, FSCK needs to access block devices to do a file system check. So that means there's a set of entitlements which are commonly called COM Apple rootless something, and they all enable you to do the effective bypass of the system profile in this way. Now about these entitlements, we've got so many of them, and I'm just going to give you some simple examples. Again, going here, I'm going to use some, I don't know, arbitrary binary. For example, if you're looking here, I'm doing this on macOS, so if you're looking at user libexec kexd. Kexd is your kernel extension daemon. This has entitlements. Yeah, for some reason it's still a i386 slice, I don't know why, but let's do x86-64. And so you see here that there's the COM Apple private get kext info that enables you to read kernel information. For Linux people, that's like lsmod. We've got COM Apple rootless kext management, and that effectively does insmod and rmod, which is kext load. And we also have some file system permissions. Whenever you see COM Apple rootless storage, that means there's some file system locations. And if you look at the various iOS binaries, and again, there's just so many here. I've got the file system open here. Just some random look at, I don't know, sbin. Or you can see, for example, here in user libexec where all the daemons are, then you'll see that virtually every single one of those is also entitled. For example, nfcd, which is in user libexec. This is the one that does your near field connectivity for Apple Pay and stuff. So you can see it's got all these host of entitlements. Now, as you can see, I'm using a tool here, jtool, which effectively looks at the binary, and that means that these entitlements are part of the binary. They're part of the so-called code signature. And that, in fact, is something that makes them strong. Because if we take as a given that code signing works, then we realize that it cannot be broken. Axiomatically, we believe it. And that means that whatever we find in the entitlements is automatically verified and vetted by Apple. And so this is the main thing that Apple now uses. And the number of entitlements have like exploded, virtually exploded. And as I point out in here, the next slide also, I maintain what I call an entitlement database. Let me just fire up Safari here for a second, which is something that I do in every version that enables you to look at the various entitlements, possessing whatever entitlement or whatever executable. And as you can see here, there's about 1193 in iOS 12, in iOS 11. If you look at iOS 12, the number actually increases to 1359. There's just like so many of those. And ironically, the IP address range that gets the most hits for this is Apple itself. So apparently Apple 17xxx, they don't know their own entitlements apparently. So we've got so many of those, and again, we have to somehow defeat them. If you can defeat code signing, you're done. If you can't defeat code signing, you've got a problem. So mostly what you would do is you'd either get code execution in some daemon that has an entitlement, thereby effectively wresting the entitlement from it, kind of like what you used to do in old Unix with setuid. You can think of it as an extension of setuid. Or if you have kernel read-write, you can start patching. And what you would patch is you would patch not one location, but two locations. The first is your own entitlement blob, which is part of your vnode, part of the file representation of your executable. So this gets loaded into memory, and that turns into what we call a vnode object, which is like an inode in memory. And that vnode points to what we call the UBC, or Unified Buffer Cache. And that Unified Buffer Cache is your little blob. And if you can get to that blob, after it's already been parsed and vetted, you can just do any type of mem copy over it and it's fine. But it turns out it's not enough because there's certain entitlements. And if you're familiar, these are, for example, get task allow, task forbid allow, the ones that really have far-reaching impact for debugging. And those are validated by AMFI, by Apple Mobile File Integrity. And so there's another cache of them that you would have to defeat yourself. Now, fortunately, this is in data and this is still doable. So how does it actually work? You've got the process list. The process list is always accessible through a symbol which is either exported, or in the new kernels, nothing's exported, but you can find it with another tool I wrote, which is called Joker. So we find that it starts at this kernproc process. The kernproc actually points to a fake process, that's your PID 0, which is also in task words, that would be the kernel task. But then this then iterates, and you can go over the list and you can find PID 1, PID 2, and all the various PIDs as a linked list. Every one of these processes is this humongous structure. This is only just a very small snippet of it. But you can see that it has, for example, your cached UID and GID. This is familiar to all the Unix people. And there's also over here in the bottom, PUCred, which used to be at offset 256, but they keep changing that because they keep modifying their fields, of course. This points to a UCred, and that UCred has your actual real UID and your real GID. So this is basically where you have 501, 501, you're going to patch that to 0. And more importantly than that, there's this thing over here, which is a label. And what is that label? This is the credential label, which then ties in to the various Mac frameworks. So this couldn't all fit in one slide, so now consider that we've got the CR label. Now this goes to a struct label, and then we've got little slots. Slot number 0 is taken by AMFI. Slot number 1 is taken by the Sandbox. Now, of course, this means that this is somewhere in kernel memory, and this is entirely patchable. So if you patch this, there's no thing that Apple can do against this patching because this is impure data, and therefore you basically get everything you want because you can automatically elevate your privileges and so forth. Again, a simple example, which I'll show you over here, because I have in macOS a simple tool that I wrote for this. So I'm just going to be root, and I'll just do snoop walk proc. This is all the process list, okay? So this is all the process list, and you can see every process here has, this is the view in memory, so there's the UID, the GID, the threads, what the thread is doing, the file descriptors, and over here we've got the AMFI slot of the cached entitlements, and may or may not have a sandbox slot. Okay, in iOS, everything has a sandbox slot. In macOS, not necessarily, because you don't have full sandboxing and everything. And then if we just look at a particular process, for example, I don't know, let's look at, KexD. So wait, where is KexD? KexD is this guy. So snoop and then dump the PID, which is usually 45, 46. And you can see right here that we've got these very same entitlements that we saw with JTool, but now they're cached as a dictionary. And also, again, no sandbox slot. If I were to look at something like Preview or some third-party app from applications, then most of these are actually sandboxed. Apple sandboxes themselves voluntarily by means of an entitlement. And those third-party applications, if you get them from the Mac store, therefore they're also sandboxed in the same way. So as you can see, if I can write a simple tool that can display this thing, obviously this would be kernel read. If I had kernel write, I could obviously patch these things just as simply. And this is one thing that thankfully there's no real solution for. So from the jailbreaking perspective, this is pretty much what we're getting to be left with. Now about this amphi. Amphi, we've already encountered as the entitlement enforcer, but it's much, much, much more potent as a code signing verifier. So whenever you do some type of exec or POSIX spawn or any type of something to start a process, then what happens is we've got amphi, and amphi is, as I say here, the sworn nemesis of all jailbreakers. It's constantly trying to make things harder and harder and harder still. So how does it do that? There's a macf hook, a call out on execve, and there's also another one on check signature. This goes to amphi. Amphi will do the validation, and the kext is going to look at two specific cases. One case is going to be what we call an ad hoc signature. The other case is going to be called a third-party signature. For an ad hoc signature, again, you can easily see that. Documents iOS here will do, I don't know, like launchd. So -- sig on launchd, any Apple binary you can see is ad hoc in that it's not really signed. It's just a basic hash. But the hash rests somewhere in the kext. For a third party, the third party is going to be with a full signature blob, and then you have to do the actual validation. Now, how is that going to work? We've got the same general flow of macf, which means system call gets trapped and so forth. Then amphi goes and looks at the trust cache, which is a region of memory that is effectively signed as part of the kext, and shows you that those particular list of hashes which are allowed. Now normally if something is not found in the trust cache, which can only be for Apple's own binaries, we have to go upwards to amphd. And that was the weakness that was exploited continuously. There's some type of code signature blob, and you may be familiar with jtool -sign or LDID -big S, so you can self-sign yourself. amphd is supposed to check libmiss, which is essentially their provisioning library, and if you can hack this, then you can say okay, this says okay, and then you can do whatever you want. And this used to be the case until iOS 12, which was constantly exploited. Now there was two ways of exploiting this. One is to go into the trust cache, specifically the dynamic trust cache from Xcode, and essentially patch it in memory. This is something that I kept saying must go away in iOS 12, must go away in iOS 12, especially after a very noted iOS hacker called Serub figured out a way and put it in open source. And so it kind of went away. In the A12, this is physically locked in memory. And so that doesn't work. But in anywhere before the A12, which means up to the iPhone 10, it totally works still. The second approach would be to debilitate amphi, and that means to essentially hook amphi with something that is basically a debugger, and you just find those callouts to libmiss, and you basically patch them. You patch them by generating an exception, returning 0, and then everybody's happy. I mean, Apple is not, but you are. And so there's a very simple method of doing this, and you can do a small daemon, which I call amphi debilitate. It sits on your device. It also makes sure that if amphd gets killed, because sometimes launchd kills processes for saving memory, then as soon as amphd restarts, it'll also, of course, do the debilitation again. That part is a major change that will affect all devices, because iOS 12 introduces a kext called core trust. Now what does core trust do? It makes sure that you can't fake sign anymore. You still sign, but now it has to be signed with one of two certificates, which is either Apple Root or Apple Developer CA, which means, you know, for your third-party apps. And only after core trust actually says it's signed, do we go up to amphi. Now what does it mean? You can still do the debilitation, but it's going to be only after core trust says there's some type of blob and some type of valid signature. So only after this we go, and that's where the debilitation will happen. The impact of this, unfortunately, is going to be that in most cases it's going to be too late. If you're developing a jailbreak, you can't just use a self-signed bin pack like you get from my site or otherwise. You have to do the signatures yourself, and it's really painful, or you have to find another way. Now as for kernel patching, that's really where the battle ranges, because kernel patching we can do, and we can either do it directly or indirectly. Usually when I get to this part I'm a little bit out of time, so I'm not going to go into the actual techniques, but Basically, the idea is very simple. You either find some Mach port or IPC object or Mach object in general that you can use, or you find an IOKit object, and specifically the IOKit object is super popular because IOKit is object-oriented and it's got vtables. So you find a vtable, you find a way to basically override a pointer in that vtable, boom, that's automatic code execution, because really what's a vtable? It's only an array of function pointers. So what you can do is, and this is what we nowadays do, we find memory, we repurpose it to create a fake object, and that's when you get effectively code exec. How much time do I have here? Ooh, not so much, so we're not going to go through this. Okay, which is a shame, because that's like my best part. But anyways, now let's conclude and talk about the hardware protections. So we now have effectively 3 equivalence classes. We've got the A7 to A9, where we've got KPP. Okay, long story short, KPP is still bypassable. A10 and later, that's your iPhone 7, that's where you've got this KTRR, which is unfortunately, as far as we know, not something that can be bypassed. And this becomes even worse with A12 devices, which I would like to focus on. So I'm going to just go briefly skip over the KPP and KTRR, because that's pretty much documented. And I will talk about those A12 hardware changes. Apple introduced their A12 chip. They called it like Neural Engine, Bionic, Amazing, blah, blah, blah. But they omitted to talk about the main changes that they put in, which are memory changes and instruction set changes. Apple is the very first implementer of ARM v8.3. And that's not just ARM64, but this is ARM64 with various enhancements. And a key enhancement is going to be this thing that they're now using, which is called PAC, or Pointer Authentication Codes. Now, what this means is that for the meantime, at least, Apple is like the first ones to do it, just like they were the first in 64-bit. It's going to come eventually because Qualcomm is one of the developers of this. So you can expect it in Android sometime by 1 year or 2 years from now. Now, what does it actually do? We have a pointer. A pointer is a 64-bit, effectively, integer. But if you look at those 64 bits, the topmost bits are sign extension. We don't use them. They're always pretty much the same. So what we do is we repurpose them, and we generate an authentication code from some type of on-CPU key. There's actually 2 of them. Okay? So we take a context, which is usually the stack pointer, so you know which frame you're in, or some type of register that the program can supply. We do 128-bit keys, and which are effectively something you cannot read in user mode. And there's an algorithm which may be implementation defined, or maybe something developed by Qualcomm, which is called QARMA. And so if you look here, you'll see that what we do is we basically generate these codes, embed them in this pointer, and replace instructions. We add a few instructions like PAC-I, or PAC-D, and this should be a PAC-D, which is to do a pointer authentication code for instruction or data, as well as auth-I, auth-D, which are authenticate that instruction code. And we also have XPAC if we want to remove it. But the main thing is, because compilers can't generate all these instructions, we can basically replace existing ones. So instead of branch and link, we have branch and link authenticated. We have branch register authenticated. We've got load register authenticated, return authenticated, etc. And really what it does is that it automatically does your authentication. And if that register value, which is a pointer, cannot be validated, you get effectively a fault. And so that means that you cannot malform pointers in this way. So just a simple example, this is from the iPhone 10, like the little iPhone X, and this is from the iPhone 11, which is the XS. You can see that it's pretty simple. The only thing that's changed here is that you've got the ret turning into a ret AB. Now there's further changes, but I think they're going to kick me out soon, so we're not going to talk about these further changes. Primarily, if I had to pick one that's going to have a far, far-reaching impact, that would be your ARM v8.3. The key management in the Apple case is not that good from what I've seen. Instead of using 128-bit, they just use the same 64-bit key twice. Okay, whatever. If you're actually looking at it, if you get your hands on an iPhone 11 kernel cache, which you can easily get from the OTA or from the IPSWA, you'll find that there's good, interesting code. It may come out in the sources, it may not come out in the sources, because Apple might decide to if-def it out, but even if it doesn't come out, nobody cares, because it's all raw inline assembly anyways. In the future, there's something even worse, which has just been approved by ARM, It's called ARM v8.5. There is also an 8.4, but nobody cares about that. That's just for virtualization. But in 8.5, this is something that actually has memory tagging and has branch target indicators. Branch target indicators means that when you're doing a switch, you're going to have a closed list of where to branch. And that effectively means that you won't be able to overwrite pointers in any constellation whatsoever. And then coupled with memory tagging, which means that you can only access memory for read and write if you possess the right tag, that effectively could really, really hinder exploits. I'm going to skip over the jailbreak toolkit that I have. Some of you might already know it, but basically this is something I've recently updated for iOS 12. And I'll just go to conclude with the main takeaways, which are, number one, iOS, this core trust thing. If you look and analyze it deeply, the effect on APTs is zero, is negligible. As an APT, you already have code execution because you're running in through an app or you got in through WebKit. It's not going to affect you. The only target of this core trust is for people who want to jailbreak. So Apple is basically targeting the wrong people. More importantly than that, the hardware changes in the A12 processors, that's going to be the main thing. Now, over time, Apple is going to phase out their old devices. It's not happening yet. iOS 12 still supports 5S, but over time it's going to get worse for the world because that means that at some point A12 will become the entry level, maybe around like iOS 15 or something, and that will greatly, greatly impact jailbreaking. Specifically, we're going to see those three equivalent classes I've mentioned, which is A7 to A9. It's all the way up to the iPhone 6S. That's going to be fairly easy. From the iPhone 7 and later, it's going to be hard because of that KTRR, but kernel data patching still works. From the A12 and later, nobody knows. So if you're looking for the when ETA of the next jailbreak, I can't promise you anything here. That's pretty much it. I just want to greet out the right people of the community. So that's, Pangu and Luca. Luca's amazing. And Serub, who unfortunately tells Apple everything that we do. So puts it in open source. And of course, Ian Beer, who helped basically develop the last 3 or so jailbreaks by providing the actual patch. And you can find more of this in the book. And if you have any questions, I think I still have a minute or two.
No.
I don't have a minute or two. No questions. Do not ask me questions. If you really want questions, you can find me. I'm going to be around here for a couple, unless they really throw me out.
Exactly.
So, peace, people.
Coffee break, 20 minutes. Go.